The logistic differential equation is a powerful but simple equation for modeling population growth under limited resources. Now, to start, we can look at exponential growth, which is described by a simple differential equation dp by dt equals rp. Here, we have a growth rate that's proportional to our population, and this results in exponential growth. However, the problem is that in real life, resources are limited, and that growth must slow as population increases. In the logistic differential equation, we solve this problem by adding a limiting factor. On the right-hand side of the equation, rather than just rp, we have this factor of 1 minus p over k. When p is small, then we still get similar exponential growth. However, as p approaches this value k, the growth slows to 0. That is, dp by dt becomes nearly 0. In this equation, r is the growth rate, the same as an exponential growth, but k is the carrying capacity, which is the maximum population. So when p equals k, dp by dt equals 0. Now, to solve this equation, we can use separation of variables. We can start by moving all the p-dependent terms to the left-hand side while keeping r on the right-hand side, since we don't have any explicit t's here. Next, we can try and simplify the left-hand side using partial fractions. We can start by multiplying the top and bottom by k to get a nicer form, and then we want to look for partial fractions in the form of a over p plus b over k minus p. To solve this equation for a and b, we can multiply through by k minus p, and then notice that when we set p equal to 0, we have that a equals 1. Meanwhile, when we set p equal to k, we have to have that b equals 1. We can plug in these values for a and b to simplify the fraction in the left-hand side to 1 over p plus 1 over k minus p. By plugging this in, we have a much simpler form that we can actually explicitly integrate, which is what we're going to do in the next step. The left-hand side can be integrated pretty simply using the antiderivative for 1 over x. It becomes ln p minus ln of k minus p, making sure to include the absolute value signs. Now, the right-hand side is just the integral of a constant, so it should just be rt, and we also include the plus c since we're doing indefinite integrals here. Now, using properties of logarithms, we can simplify the left-hand side to ln of p over k minus p, and now we can exponentiate both sides to remove the logarithm and solve for p. Now, e to the rt plus c is just going to be e to c times e to the rt, and using the fact that e to some constant is just some other constant, we can write this as a e to the rt, where a is our new constant. The left-hand side also simplifies because e to the ln x is just x, and so we'll get p over k minus p equals a e to the rt. Now we can simply solve for p using a bit of basic algebra, and what we'll find is that p equals k over 1 plus a e to the negative rt, where k is our carrying capacity, a is our constant, and r is our population rate of growth. We can plot the solution on a graph of p versus t to see how it behaves. Near t equals 0, where p is still small, we see that the growth is pretty much exponential, as we should expect. But as p gets large, it sort of reaches a horizontal asymptote, and it never exceeds k. This S-shaped curve is known as a sigmoid curve because it starts with exponential growth and slows as p approaches k. This solution to the logistic equation is incredibly useful in multiple fields. Because it includes how growth should slow as populations grow, it models realistic population growth, accounts for limited resources, and is used in ecology, epidemiology, and more. Thank you for watching.